Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Today we continue our exploration of trust in AI with this interview with Richard Zemel, professor in the Department of Computer Science at the University of Toronto and research director at the Vector Institute. In our conversation, Rich describes some of his work on fairness and machine learning algorithms, including how he defines both group and individual fairness, and his group's recent NeurIPS poster, Predict Responsibly, Improving Fairness and Accuracy by Learning to Defer. Thanks once again to Georgian Partners for their continued support of the podcast and for sponsoring this series. Georgian Partners is a venture capital firm that invests in growth stage business software companies that use applied artificial intelligence, conversational AI, and trust to differentiate and advance their business solutions. Post-investment, Georgian works closely with portfolio companies to accelerate the adoption of these key technologies for increased value. To help their portfolio companies hire the right technical talent, Georgian recently published Building Conversational AI Teams, a comprehensive guide to lead you through sourcing, acquiring, and nurturing a successful conversational AI team. Check it out at twimlai.com/Georgian. And now, on to the show. All right, everyone, I am on the line with Rich Zemel. Rich is a professor in the Department of Computer Science at the University of Toronto, as well as being research director at the Vector Institute in Toronto. Rich, welcome to This Week in Machine Learning and AI.
Thanks very much.
It's great to have you on the show. I'd love to get started by hearing a bit about your background and your path to your work in machine learning.
Sure. So I've been interested in machine learning, or I've been interested in artificial intelligence for a long time. In fact, since high school, I got lucky and had a summer job, and I was growing up in Pittsburgh and had a summer job at Carnegie Mellon, working with my next door neighbor was named Hans Berliner, one of the original person who wrote game playing programs for played games like backgammon and checkers, and had some of the original ideas that later, led to some of the ideas in chess and Go, the famous game playing of these days. So I've been interested in it since that time, and worked for companies back in the 80s, artificial intelligence companies back in the 80s, when the AI winter first hit. So that was my first experience with AI. Went to graduate school after that and got my PhD in machine learning. Finished in the early 90s, and I've been working in it ever since.
Oh, fantastic. And I mentioned your post with the Vector Institute in Toronto. Can you share a bit about what the Vector Institute is up to there?
Happy to. So the Vector Institute is an independent nonprofit institute that's a combination of academia and industry. So there's a lot of faculty members here who have their home in universities such as University of Toronto or Waterloo or Guelph, and as well as more distant universities like Dalhousie and UBC in Canada. And those people are all doing machine learning research. We also have some research scientists their primary employment is here at Vector. And there's a lot of graduate students and postdocs associated with Vector or affiliated with Vector, all doing research in machine learning. And so that's my focus is the machine learning research side of it. But there's also another very strong side of it, which is industry, and working with industry and trying to help industry grow in terms of their machine learning capabilities. So Vector has funding from the federal and provincial government in Canada, as well as a lot of industrial sponsors to help the kind of industrial business side of machine learning, as well as the research end of it.
Now, I've taken a look at some of your publications, and you've got a pretty broad, what appears to be a pretty broad set of research interests. Can you talk about, where you tend to focus and some of the things that you're working on?
I've been interested in some of the kind of longstanding problems in in machine learning and in AI in general, like, scene understanding is an example, right? So how can the computer really understand what's in a scene? How can it pick out, somebody saying something of interest to you across a crowded room, or find your friend in a crowded bar? I mean, so it's like, the kinds of things that we're quite good at have been hard for computers for many years. So that involves good learning, so taking in lots of data and trying to find patterns in it. And one of the things we've learned over the years is that the important thing that machine learning can add to this is the idea of learning good representations for inputs based on the data. So any kind of learning of representations that involves what's known as unsupervised learning, where you may not be told what to take out of the data, you just try to do it. The system tries to figure out itself what are good features for the learning. And so that's my research. And more recently, I'm interested in things where the aim is to come up with what we would call a more structured representation, something where the human has some input into this and can define what it wants. So it can say, for example, we know that there's going to be, if we want to recognize a face, that there's going to be certain features of the face that we think are important. So you kind of, the human is giving some hints that the computer is then going to use. And we've made a lot of good progress on these kinds of things, I think, much more so than I originally thought in some ways. I thought it was going to be a long way off, but we're making a lot of good progress in this area.
Mm-hmm. That example you gave about the features in the face, it does kind of resonate with this trend that I'm seeing in machine learning research, where we've kind of started with these models that, in many cases at least, are very much grounded in the physical world. And in the case of computer vision, kind of feature detectors and edge detectors and things like that. We kind of swung to the other end of the pendulum with deep learning, where we don't explicitly do any of that stuff. And now more and more we're kind of trying to find a middle balance where we're incorporating in our knowledge of the physical world, but still trying to use the power of deep learning. Does this work fit into that mold?
Exactly. So I think that so for an example, something that we've recently made a lot of progress in my group and many other groups is where the input to the learning system isn't just like an image or something or a sound bite. Instead, it's something that is represented as a graph. So you have nodes and relations between the nodes. And so then so you have some sort of, that's what I meant by a structured representation. And the ideal is that then you can learn from that. So you're kind of given some sort of information that's, not starting from the basics. But so given that, we're able to do a lot of interesting processing on top of it. So I think that's something where it's combining some kind of information that humans have in a lot of different forms, right? We have know about objects and their relations. It could be in big databases or, descriptions of the world. And then we can learn from those on top of it. And the biggest challenge is not to start with that kind of relational information, but try to learn it as you go along. So that's the kind of the frontier, I would say, in this area.
And then you've also have an interest in fairness in machine learning and have published several papers in that area. Can you talk a little bit about your work there? For example, I noticed you've got a paper that has been accepted to the upcoming NeurIPS conference that we'll both be at in Montreal. Maybe we can start with that one. And I'll interrupt if you would like to kind of broadly, contextualize your interest in that space and your the kinds of things you're working on. We can start there.
So I'd done some other work with some colleagues on fairness and was invited to a workshop a few years ago in Washington, D.C., where the discussion was about computer algorithms in the courts. And so this was a workshop that had people studying civil rights and as well as people from the legal system, judges and lawyers, as well as some more people who are more on the activist side of things, like the Million Hoodies group. And so I think it was quite an interest, and then there were some computer science people, and so it was an interesting workshop. But one of the things I learned, and a lot of debates there, one thing's about how much influence computers should have in those kinds of things. So I learned a lot at meeting about how computers are being used to set bail and for sentencing, or at least to give advice. The kind of thing like I learned about a system in Pennsylvania where there was the input to the system was a description of a defendant, and the system would then come up and say, what's the probability that that person is going to commit a violent crime in the next few years? Right. So these kinds of systems have become quite publicized in the popular press. But this one was one that was developed specifically for the state of Pennsylvania. And it was intriguing to me because it came up with some probability, like it would say probability of 0.7, this defendant is going to commit a violent crime. And then the question is, what does that mean to the judge? How does the judge use it? And was that number really meaningful? Right. So one question
and you said the input was what?
A description of the defendant, something about the defendant's history, and it wasn't that clear. They said they weren't able to get access to too much information about the defendant for various either privacy reasons or just not having enough information. So it would be things like what kind of crimes the person has committed, what they were arrested for, what they've already been convicted for, that type of thing. And the shocking thing to me was just how little validation had gone into the system, right? So there wasn't a real sense that they had tested the system and said that 0.7 really meant what you'd hope it would, which would be that that in some unseen data, 70% of the people who were assigned of probability 0.7, 70% of those people actually went on and committed the violent crime, right? So you'd like to have some, so we call that calibration, right? That's a well-calibrated system. And in talking to the people who developed it, they said there really wasn't that much enough data, and the data was quite noisy that they couldn't do a very confident job of calibrating it. And so I was very surprised to find that this was actually in use in the court systems in Pennsylvania. So my reaction was, well, we got to do a better job if we're machine learning people. This is at its heart, a machine learning problem. So we should be working on this and trying to figure out how our systems can interact better and do a better job working in this. So that inspired the paper that we have in the upcoming NeurIPS conference. We call it Predicting Responsibly. Here, a machine learning system isn't making the ultimate decision. It's more of an assistive tool. It's something that's providing an input to someone like a judge or a doctor or whatever it might be. And so you want that assistive tool to produce information that's useful to the final decision maker. And so what we were doing in this case was saying, imagine that the tool comes out and says not yes or no, this person is going to commit a violent crime, but it could, it's not going to even produce a probability because it's unclear what a judge or somebody might do with that probability. But a simpler problem is to say yes or no, or kind of pass, and just pass that information on and allow the judge in this case to make the decision more clearly, so on their own. So it's kind of like an initial system that's doing a cull, kind of saying yes, or narrowing down what the next step the decision maker would have to pay attention to. That could be useful in a lot of settings, like when there's too many inputs and you want too many applicants to a job, and you want to have some initial culling system. But the key is this culling system, the first system that we're building, has to be fair in some sense. It has to not just try to be accurate and say yes or no, or pass it on, but try to take into account information about the defendant in this case that would explicitly try to not discriminate against that defendant. And that could be based on society definition of what discrimination is, right? So discrimination could be based on race or ethnicity or gender or various things. So that's what the area of fairness is about, is saying that you're training up a machine learning system and you want it to make decisions that aren't biased against any particular. And most of the work in fairness has been done where that particular group is defined ahead of time, right? Like I said, it could be race or gender or or age or whatever the attribute may be that you want to be fair to and prevent discrimination against. So that's what the aim is in general in fairness. And that's what we hope in this particular system, is that when it makes the decision to say yes or no, or to pass it on, it's making those decisions in a way that is fair, that's taking into account and making decisions that are ensuring that there's not discrimination against the what we call the sensitive attribute.
Yeah, we talk a lot in machine learning about how important problem definition is. And just listening to the way you are describing this system, and it's clear that a lot of the path that you take is set out by how you define the problem, more so, perhaps than even in some other areas. Have you learned or observed anything about that particular challenge as applied to this space in your work?
Yeah, so you've hit on the kind of key question in this work, which is about how do we define it. And I agree that's in general a machine learning problem that's often not paid that much attention to, in the sense that we're used to machine learning defining classification problems, or something like image classification. Is this a hippopotamus in the image, or is it a dog? And for that, you could say, well, there's a right answer, and you can judge whether there's a right answer or not. And so that's just not. But the answers you get depend a lot on how exactly you score your answers, right? So is it important to, is it better to say this is a hippopotamus if the right answer is a rhino than to say it's a dog, for example? So if you have a scoring function that's sensitive to how similar the classes are, then you'll get a very different learning system than if you use a definition of an error that isn't sensitive to that. And that applies in spades when we come to the area of fairness, because it's an area that, so I started working on it about 6 years ago. My wife, Tony Patassi, and I spent the summer with Cynthia Dwork and her colleagues and Microsoft Research in Silicon Valley. And we were working on trying to come up with, we landed on this problem of fairness, and we worked hard on trying to figure out what is a good definition of fairness. We spent the whole summer debating it. And we ultimately wrote a paper where we came up with two different definitions. So this is with Omer Reingold and Moritz Hart, in addition to Cynthia and Tony and myself. And we wrote a paper where we came up with like a group definition of fairness or an individual fairness. So a group definition of fairness would be one that would say, overall, for example, a decision is fair if, let's say, the two groups have the same number of positive outcomes assigned to them. Okay, that's a very simple thing. That's like a kind of thing like affirmative action gets at, right? So if you want to give admittance to a school, we have to say that the same number of males and females should get in, right? So that's group fair. That's an example. And then there's kind of more at the individual level of fairness, is saying, well, what you really want is for an individual that other individuals that are similar to that individual should get the same outcome, the same decision, right? So that's more on the individual level. And since so that we wrote a paper where we had that and talked about various ways of carrying that out. And in the main idea was that when this decision is made, it should be aware of whether the person belongs to that group. So we called it fair through awareness. And in the years since then, there's been a lot of debates about what the proper definitions are of fairness, and like different kinds of group fairness and different types of individual fairness. Somebody wrote a paper about the 21 definitions of fairness. So exactly like you said, defining it is the key problem, and that's what makes it very interesting and challenging. It's a fun area to work in, partly for this, because you can come up with a definition, debate whether it's right or wrong. I would say in the end, none of them are actually right, but some of them are less wrong than the others. And
so in the paper that you were describing, one of the things that I kind of zeroed in on quickly in your description was this system is designed to output yes, no, kind of almost sound like yes, no, maybe, yes, no, pass in particular, where pass is deferring on making a decision. And the idea there is to, with the pass, presumably to kind of recognize the system's own uncertainty?
Yeah, so it's a combination of things. So people have worked on the idea of what's called rejection learning in the past, and that is, saying, well, we can say I don't know or pass when the system's not confident, right? So back to the idea of, the defendant going to commit a violent crime? Well, we can say pretty confidently, within some error bars, it's going to say yes or pretty confidently no, even though you can see in those cases that confidence is it's a little hard to assess. But and there might be a big space in the middle of between those two where the system isn't very confident. And so the idea would be that if I don't know, it gets passed on to the next to the decision maker. But in our work, the idea was that we aren't going to just pass on based on uncertainty. We're going to pass also taking into account what we know about the downstream decision maker. So imagine that the system is trained up on judges' decisions, and it's also trained up on, or in a doctor case, right? It knows a lot about the doctors, and so it's going to say, taking into account the kinds of decisions that the judge or the doctor tends to make, and what kinds of problems they're accurate on, what kinds of people they're fair or unfair to, that could influence our machine learning system when it wants to say pass versus yes or no. Okay, so that's the key idea. So it's going to defer when it'll be smarter in terms of when it defers based on knowing something about what's going to happen downstream, and not only smarter in terms of being more accurate, but also less discrimination.
So specifically, the system, if it knows that it doesn't have a high degree of certainty about a particular decision, but it knows that the decision maker is worse in a particular category of decision making, it might make the decision anyway. That's right.
And so that's on the accuracy side. And it could be that if it's not very confident, but this person happens to be, in this protected set, right? So it could be of a particular gender or something, and it knows that this particular decision maker happens to be discriminatory against that group. It can decide to make a decision rather than deferring to the downstream decision maker.
Another thing that jumped out at me here is, I think in the context of kind of these examples with the courts, if you think about this relative to thresholds and, say that the yes represents some kind of, guilty or something with negative implications, right? So guilty or higher bail or longer sentencing or what have you. The threshold band that I might want to attribute to a yes is going to be maybe different than, what I would attribute to a no, because it has a much greater human impact. Does the system account for that at all?
Certainly. So that goes back to our definition in some sense, or what we would call the loss function, right? So it could be that making certain kinds of errors are worse than others, right? So making a false positive, someone would say like letting somebody out of jail when they are going to commit a violent crime, potentially is worse to society than locking up an extra person who really shouldn't have been locked up. That's debatable, right? But I mean, again, so it's a lot of these decisions are kind of these definitions have to come from society. And so, certainly on the machine learning side, it has the flexibility to do that, to say, what certain kinds of errors are more costly than others, and to set the thresholds appropriately. But that does lead to these questions about, how are we going to decide, who does, what kind of errors are more costly, right? And so that's I think something that society has to weigh in on. Similarly, what kinds of attributes do we want to not discriminate? What kinds of people do we not want to be biased against? Is another kind of question. So part of the aim here goes back to what we were saying earlier, is that we really want to add my view is we're trying to add some knobs to a decision-making system. So a machine learning system that adds some knobs to a black box so that society or other people can come in and add some control, have some insight into what's going on, and add some control to it. And so it's control in this way by, like you're saying, it could be that certain kinds of errors are more important, and it could be that we want to reduce the bias against this group or that group. And what does that actually mean?
I'm curious, for the decision maker, the system has to have you've got to be able to represent the decision maker's decisions in some way. Are you providing it a distribution or a set of rules or something else?
Well, the decision maker is going to make its decision, based on whatever features it was originally going to make its decision. So at least the way we formulated the problem is that our system is either going to make a decision, yes or no, or pass it on. And when it gets passed on, then the downstream decision maker, gets to look at the case and just review it on their own. So they get the same kind of input features they would have anyways. Another work that we've done in the fairness approach is that we're actually taking a little bit of a different tack on this. We're saying what we'd like to do is change the representation, so come up with new features that could be used by a downstream decision maker. So that's not this particular paper you were talking about, but other work that we've done in this area is about that, is about constructing a different representation of somebody so that the downstream decision has our own representation that we've constructed available to them rather than the original representation.
But in this paper, the model is learning based on some observations from the decision maker. And so I guess my prior question was, are we handing it some kind of representation of the decision maker in the form of a set of rules or a distribution, or is it more like an active learning thing where it's actually observing, independent, I don't know, coin flips or whatever? I guess it's still a distribution of some sort.
I mean, yes, you're right. There's lots of different ways we can formulate what the downstream decision maker's doing. So the way we're thinking about it would be that imagine that there's a database available of, some data set available of this downstream decision maker or decision makers and how they've responded to cases in the past. So that's kind of a separate training set. Okay. That we're observing that, and we're taking that into account when we build a model of what's the decision maker likely to say for this new case. And then that's when our system is deciding yes or no or pass. It's using the model we've developed separately of that downstream decision maker.
And is this system, is it something that you've implemented? Is it something that you've modeled mathematically? Like how? Yeah,
so we don't have good data for this. It's very hard to get, it's something that we've implemented, and we've, like often happens, unfortunately, in this fairness area, is that there aren't great data sets out there. There's very few. There's one that's well known as this COMPASS data set, which is a data set like I was talking about that looks at this exact case of here's a defendant and what's the probability, and the system's aim is to come up with what's the probability that person's going to commit a violent crime in the next 3 years. So that's a very well-known data set. Some of the other data sets that are in use are ones that we've actually constructed ourselves, where we'll take an existing data set and then we'll make it into one that's relevant for fairness by identifying some sensitive attribute. Like we'll say there's one known as the adult income data set, where you're trying to decide the decision to be made is this person going to, is their income greater than $50,000 or not, right? So that could be useful for loans or whatever. But we made it into a fairness data set by taking one of the attributes, gender, and the gender of the person, and saying we want to make sure that the decisions are made are not only accurate about the income, but are also fair with respect to gender. So we take existing data sets and make them relevant for fairness by identifying one or more attributes that are, the relevant things for preventing discrimination. So that's what we did in this case, is that we took some existing data sets and implemented it. And then what we had to do, though, we had to simulate the downstream decision maker. We had to make up, what is this downstream decision maker? And so we tried to think of 3 different cases. One case is a downstream decision maker that has more information available than the system we're building, right? So imagine it's a judge, and the judge gets to not only get the same kind of information our system does about the defendant, but also gets to, see the person face to face and ask the person questions and gets additional information about the defendant that way. So in a way, it's a more knowledgeable judge. But let's say that judge doesn't care about being fair. Okay, just wants to make his or her best decision. So that was our model of one version of a decision maker. We had other ones too, ones that were intentionally unfair, ones that were intentionally discriminating. And so what we did is we trained up our system based on these different simulated downstream decision makers and then observed what would happen.
How do you characterize the results?
So the results I would characterize as saying that it depends what you want to compare to, right? So an interesting comparison is to say, how would we do if we could force our system to make a decision. So there's and not allow it to defer, right? So that's a kind of standard machine learning classification problem. We kind of take the decision maker out of the loop and just use our system. The other version of it is one where we take our system out of the loop and just use the ultimate decision maker, right? So those are the two extremes. And then we have different versions of our system, one of which just says, I don't know, without paying attention to what it thinks about the downstream decision maker. And then the fourth is the kind of ultimate goal, which is what we wanted to really propose, which is this idea of learning about the downstream decision maker and taking that model into account in making our decisions. And in general, and we looked at it in these different scenarios, and in general, the effect was what we wanted, in the sense that we were able to achieve a pretty good trade-off of fairness and accuracy using the system as we had formulated it. Certainly better than either just relying on the downstream decision maker or relying on our system alone. But and the interaction where we were able to build a model of the downstream decision maker that was pretty good, did improve overall, both in terms of accuracy and fairness.
I came across another paper that you worked on recently, learning adversarially fair and transferable representations.
Yeah.
Can you give me an overview of that one?
So that one is along the lines of what I was mentioning earlier, where the goal now of the system isn't necessarily to make a decision, but rather to come up with a representation. So this fits in with what we were talking about early on, that machine learning systems, one of the big advances that we've had is in coming up with representations, right? So learning good features for visual recognition or for speech recognition. And so this is along those same lines. And so what we've worked on for several years is what we call fair representations. And that is coming up with representations for, let's say, individuals in this case, rather than images or sound bites that are fair in some sense. So, and obviously, again, it depends on what your definition of fair, but one intuition there would be, what we'd like to do is have a representation of an individual that is clean that doesn't have any information, that kind of obfuscates any information about whatever the sensitive attribute is, right? So, for instance, we'd like to come up with a representation of you where it's not clear if you're a male or female, because if we want to ensure that any classifier using that representation will not be able to discriminate against you based on your gender, then we want to remove all information about gender in the representations. So then that will ensure that the downstream classifier won't be able to make a decision about you based on your gender. So that's the notion of fair representations. You kind of remove any information about gender before handing off that representation to a classifier.
You mentioned an image previously. Is that typically the domain that you're working in for these fair representations, like something that's characterizing, that starts from an image of me and then generates a genderless or raceless image? Or is it more abstract, like you're looking for some embedding space that, isn't correlated with, race or gender or things like that?
Yeah, so it's more the embedding space that isn't correlated with race or gender. And generally, so far, we aren't starting with, though the original representation isn't an image. It's, think of it as a database record of your demographics or something, right? It's about where you live and how old you are.
Mm-hmm.
And so something that you might be used in, in another kind of setting that's not based on images or hearing your voice or anything. So it's, a typical kind of, let's say, demographic record of an individual. And what we want to do is take that demographic record and construct a representation of it, like an embedding of it as you described, where that embedding has lost information about your gender or your race or something like that. Okay, so that's where the identified attribute, we've removed information from that. Okay. So that's the idea of the fair representation. So our paper now, it's a paper with David Madras and Elliot Krieger, and as well as Tony and myself. And that paper, the idea was exactly as you described. So you want to create an embedding that doesn't have information about that attribute. Let's say it's gender. And the way to do that is to construct an adversary, where the adversary is going to take the representations or embeddings that we construct and try to pull out the information to figure out what is the gender of that individual. So we're trying to create a good embedding that will thwart this adversary, make it impossible for it to pull out that information. And the interesting thing about this is, so that idea is, as this adversarial approach, but we can then come up with there's been a bunch of definitions of fairness that have gone beyond the original kind of group fairness that we described. And so one of them is called equalized odds. Another way of saying that is you can think of it as a balanced errors. So rather than making decisions that are balanced between the two groups, like 60% of the people of the males and females are going to get in. Instead, another criteria for fairness is that you want that when the system makes an error, those errors are balanced. So, whatever the errors are, half of the errors are for males and half of the errors are for females. Or, if they have the same kind of base rate, or, if there's 70% as many males in the database as females and 30% females, then 70% of the errors are males and 30% of them are females. Okay, so that's a different fairness criteria. And we can adjust our adversary to reflect that fairness criteria. So it doesn't have to be that. So it could be that it's only going to try to extract the information about gender on the error cases. Okay, so and we want to thwart the adversary from doing that. So all I'm saying is that we can kind of tailor our system, our adversary, to different definitions of fairness and then train it up in that way. And so that's the main idea in what we call laughter, the learning adversarially fair and transferable representations. And the key notion is that, so why do we want to come up with these representations that are fair, is that this transfer idea. So it might be that we want to use that same representation in other settings. So we might want to say, now I have this individual, I've taken your demographic information, I've taken out your gender information, and now I want to see if, and now maybe many different advertisers may want to decide whether they're going to advertise to you or not. And by making this new representation that doesn't have your gender information, we're ensuring that all of those different advertisers, when they work on that new representation, won't be able to discriminate based on your gender. So that's the transfer idea, is that we could take that same representation and use it in different settings for different kinds of classification problems.
And have you come across anyone doing something like that in practice? Identifying some representation that is fair in this way and using that for downstream decisioning?
I've talked to a number of people in companies where they're certainly concerned about fairness and trying to ensure that they have a classification system that is fair. And so, they're interested in this idea of having a representation that would be kind of, that you could give a stamp of, a fairness to that representation that they could use in multiple settings. I don't know if anybody who's actually using that idea in practice, but certainly there are more and more interest in companies where they want to be able to assess to what extent is their system fair that they're using, and improve its fairness. And so I think this notion that you have a representation that could be used for multiple settings, multiple problems is of interest to people, but I don't know of anybody actually doing that yet.
You mentioned the assessment piece. So this can be used, this method could be used for assessment independent of whether you're actually using these kind of representations downstream, right? That's
right. I mean, you can evaluate the kind of, based on whatever definition of fairness you might want to have, you could say, how well does this, to what extent is this system violating that, right? So it's kind of like gives you an ideal that says that, are the errors, the one definition I mentioned, this balanced errors definition or equalized odds, you can say, how much is our current system violating that? It's a little bit hard to quantify, to the degree, but you can say, on what percentage of the cases is it violating that, or so certainly people are interested in this notion that you can kind of audit an existing system and say, how well is it doing based on various fairness metrics.
So we've talked about a couple of your recent papers in this space. Can we take a couple of minutes and maybe get your perspective on the broader landscape around fairness and machine learning and what some of the big challenges and opportunity areas are?
Yeah. So I think of fairness as a kind of interesting microcosm of machine learning in general, right? So some of the same ideas we've talked about adversarial ideas is reflected in general in machine learning, trying to come up with representations that either separate out, or in our case, reduce the information in a particular case. And I think that's true of in general about the rest of the fairness work these days. So one interesting bit of work I would highlight is unfairness and causality. So in general, machine learning is very good at pulling out patterns and saying what aspects of the data are correlated with some label we might want to give. But there's a big push now to try to come up with more causal reasoning. So it's not just that things are correlated, but they're actually causal. And that would enable us to do what's called counterfactual reasoning, right? So not only if you have something that's causal, you could say, well, what would hypothetically happen if we flipped that bit in one of our causes and changed it? What do we expect to happen, right? It's a big challenge for the field because generally that means that kind of data isn't available in most cases, and so it's there aren't great data sets for it, and it's something that's but it is an aim that's generally true in machine learning. And I think it's really important for the case of fairness because understanding the underlying causes for why some decision is made may be an important step to try to reduce discrimination. So that's I think a very, very interesting area of research. We actually have a paper in that direction coming out at the next Fat Star conference, but I think there's been great work in the field, some number of papers on things called counterfactual fairness and other areas, and other kinds of papers in that. So that's one thing I would say is causality. There's another one, which is there's a simplification I've mentioned, which is that you have a single sensitive attribute, like it's gender or race, and in the real world, we know there's many sensitive attributes, and we might want to be ensuring that the system is fair with respect to several at a time, and that in itself is not easy. So there's some nice work out of Stanford and some parallel work out of Penn, research groups, with something they call fairness gerrymandering, which is, it's a cute name where it means like you can be fair with respect to one dimension, and that may make it less fair with respect to another. So how can you simultaneously be fair with respect to several attributes? So I think that's a important and interesting area. And
it also makes me wonder if some of the recent work happening around multitask learning could be applied in this space.
Yeah. So I think the multitask learning was part of our inspiration for the laughter thing, right? Which is transferability, right? So you want to have the same representation that's useful for multiple tasks in that case. And I think the multitask, in this case, it's kind of harder than multitask. Though I think when you have it's multi-attributes, you want to be fair against all these different attributes. And the real challenge is that it's kind of like it's also related to these other areas of machine learning. Like I said, that I think it's a microcosm of machine learning. There's a lot of work in few-shot learning where you want to be able to learn with little data that's available, little labeled data. So it may be that you have some attribute that you want to learn, that you want to be fair to, but you have very little data available for that. So how can that really taxes a machine learning system, right? It's very hard to do that. And then there's the kind of big open question. Maybe we don't really know what attributes we want to be fair to. So rather than humans deciding that it's gender and race that are important, it could be some other group that's actually being discriminated against. And how do we, so that's a bigger kind of open question of, undefined attribute discrimination. And people are thinking about that these days as well. So I think those are some of the main areas, I would say, in fairness that are currently of interest. And like I said, there's a lot of work that's paralleling what's going on in other parts of machine learning in the fairness literature.
Any recommended starting places for folks that want to learn more or dive more deeply into this area?
I know there's a book that's being put out by Solom Barakas and Moritz Hart on fairness they've developed. It's online. It's available. There's a number of very nice invited talks from people. Kate Crawford gave one at NeurIPS last year. And in terms of papers, I think there's a fair number of papers that are looking at the definitions of fairness and interesting questions about incompatibility of fairness. So some work there. John Kleinberg with some colleagues has some papers. And so I would say that in these days, what's interesting is it used to be there were 1 or 2 papers on fairness a year. Now, if you go to a machine learning conference like ICML or NeurIPS, you'll see there's 5 or 6, at least maybe 8 or 10 papers these days. So, I think picking up some of the recent papers in any of these areas is a good starting place. So that's be my recommendation.
Well, Rich, thanks so much for taking the time out to chat. I really enjoyed it.
Sure. Been fun. Thanks.
All right, everyone, that's our show for today. For more information on Rich or any of the topics covered in this episode, visit TWiMLAI.com/talk/209. Thanks once again to the great folks at Georgian Partners for their sponsorship of this series. Be sure to visit TWiMLAI.com/Georgian for more information on their Building Conversational AI Teams guidebook. As always, thanks so much for listening, and catch you next time.